so this was as far as we wanted to talk in a general way about what are the qualities of a descent direction. The next thing that that I will briefly mention, but we will not cover in detail in this course, is the second family of algorithms. First family is line search methods. Second family is trust region methods. So the trust region approach is kind of a complement to the line search. In the line search, I'm trying to find the correct direction to go to. In a trust region, what I do is, has two steps. The first step is I construct an approximate model of the function. Okay, so what does that mean? Let us say I have a complicated function that I cannot even write as sine, cos, tan, log, whatever, right? It is something that is coming from data. But so supposing I give you a bunch of points, supposing I give you a points like this, right? Okay, that's too complicated. Let's just do this. Supposing I give you a bunch of points like this, and I say make a model out of these points. What would your first instinct be? If you wanted to do the simplest possible model that explains this data, what would you do? Fit a quadratic, right? If I take a quadratic expression, I'll get something like this. There will be some error somewhere, but this reasonably explains the data. Once I get what is the advantage of building a model? I can do continuous math with it. I can take derivative, I can take second derivative, all of those things I can do, right? And all the time I have to keep in mind whether or not how accurate this model is depends, I mean that translates to how accurate my analysis is. So step one is quite simple, is construct a model, let's call a model of the function, let's call it mk, okay? And I mean obviously the objective of this is it should match the function behavior in some region, right? So again, like in the parabola, if I can fit a parabola in 1D, I can fit a quadratic form in n dimensions. The idea is just the same, right? The next thing is, the second and final step is, now search for a minima of this model in a neighborhood of xk. Search for a minima of mk now, not fk, in the neighborhood of xk. Okay, so what does the optimization problem look like? Now I am trying to search for, give me the best p such that mk xk plus p. So I have my model mk which explains the function behavior near xk, okay, for example a parabola or whatever, and I say now let me add a little bit of p to this and give me the best p, right? So in some sense I'm looking for the direction, I'm not, it could be any p, but if I sort of don't put any constraints on this, I'll be in trouble because this model is accurate only near xk. So what I will do is such that xk plus p, okay, this belongs to some trust region T. That's where the word trust region comes. Trust means I trust the model in that region and I hunt for p's in that region, okay. So this is in a nutshell what is the trust region approach. It doesn't look radically different from a line search approach, right? I mean there are lots of similarities. That's why we will not also cover this in the course. If you understand line search, you can easily apply that same analysis to trust region. And what are the ingredients that we are working with? Essentially Taylor's theorem and legitimacy of descent directions, which also came from Taylor's theorem. So that's really the only thing over here. I'll just make one note. What is the most common model that people use in the literature? Quadratic model. Okay. So most common model would be xk plus p. So it's just going to be fk plus grad fk transpose p plus half of PK transpose BK PK. Now what is this BK? BK is the Hessian or an approximation of it. I may not be able to get an exact thing. So this is the Hessian or its approximation.